Okay, now that we know a little bit about integrals, we're ready to learn integration techniques so we can actually do them. And the first thing we're going to learn is what you might call the four elementary integrals. These are integrals that occur very commonly. We're going to use them over and over again. The first integral is the integral of x to the n, where n is going to be an integer. The second is the integral of e to the x. And the last two are the integrals for sine and cosine respectively. We could derive these formulas, although I'm not going to, so we're going to think of them just as formulas for the time being. Two things I want to draw your attention to. First, notice that all of these formulas have the constant of integration because these are all indefinite integrals. The second thing I want to remind you is that you can check one of these integral formulas by simply using that fundamental theorem we had for taking the derivatives of integrals. So suppose I wasn't sure, for example, that the integral of sine was minus cosine. I could just take the derivative of both sides, and it would have to be the case that sine of x was equal to the derivative of minus cos x, which I know is true. Okay, sometimes that comes in handy. Now we're going to learn three main methods for doing integration, and the first is called change of variables. And I want to illustrate how this method works by showing you an example, because I think if you see how it works in the example, you'll understand the concept behind when we use change of variables. So suppose we want to integrate the function e to the 5x from 0 to 3. Okay, so we go to our four elementary integrals, and we notice that it doesn't have the form of any of them. So what do? We can't do this integral at this point. But you notice that it's very close to the form for the integral of the exponential function. But the problem is we have a 5x instead of an x. So this kind of motivates the introduction of a new variable. What if we could just make this whole thing a variable? Then the integrand would have the form of one of those elementary integrals. Okay, great. However, you notice that we need to do more work, because in order to have the form of one of those elementary integrals, the differential also has to be d of capital X, and right now it's d of small x. So what I'm going to do is I'm going to start off with my change of variables. Capital X is equal to 5 times small x. I'm going to take the derivative of both sides with respect to small x, and I'm going to simply multiply both sides by d of small x. And when I do, I'm going to get this result right here. And notice now that I can actually solve for d of small x. And of course, that's what I want, because now I can substitute in for d of small x, and I have it in terms of d of capital X, which is what I want. But you notice that in addition to changing the integrand and changing the differential, I also have to change the limits of integration. So how do I do that? Well, I simply figure out what capital X is for each value of small x using this change of variables formula. So notice that when small x is equal to 0, capital X is equal to 5 times 0, which is 0. And when small x is equal to 3, capital X is equal to 5 times small x, which is 5 times 3, or 15. So you notice that now, having changed the integrand, having changed the differential, and having changed the limits of integration, we now have it in one of our elementary integral forms. And I can do this integral on the right-hand side because it has one of the forms that we know the integral of. And so this is commonly how change of variables is used. We look at the integrand and we say it looks a lot like one of the elementary integrals, except for this one part that's messing things up. If I could just make that a new variable, then I could do the integral. And that generally is what motivates change of variables. Now sometimes it's a little more subtle. I'm going to show you some examples where You have to be a little more clever, but that's often what's behind change of variables. So let's go ahead and look at some common integrals we can do using the change of variables approach. First of all, if I look at integrating tangents and cotangents, let's start with tangent. I'm going to write tan as sine over cosine. And I'm going to notice that if I let u be equal to cosine x, then I know that du is equal to minus sine x dx. And this tells me now that this integral has the form for sine x dx. I'm going to put in minus du over u. And I know that that's just the natural log of the absolute value of u plus c. And all I have to do is substitute back in for u. And I get the integral formula for tan x. And I claim you can do the same sort of approach for cotangent. I'm going to let you do that as an exercise. Now what's interesting is we can also do powers of tangent. Notice that, for example, if I look at the integral of tan to the nth power, I can factor it as tan squared times tan to the n minus 2. And I can rewrite tangent squared as secant squared minus 1. And you notice now that when I express this as two separate integrals, if I let u equal to tan x, I know the derivative of tan x is secant squared. So du is secant squared dx. And so now I notice that this integral has the form of a polynomial, plus this second integral, which I'm not concerned about because I've reduced the power. Okay, so if I can solve this first integral, the second one I can do the same way. And I know how to integrate polynomials because that's one of our elementary integrals. I do that. And now I have this second integral. I substitute in for u in the last line. And notice that even though I still have an integral left, I can keep doing this same technique over and over and over again, right? This is sometimes called a reduction formula. It's a formula for recursively reducing the power of a function. And eventually, I'll either get down to tan to the first power, okay, or I'll get down to tan squared, okay, which will be easy to do because I just then let tan squared be equal to secant squared minus 1, and I can integrate both of those. And I claim you can do the same sort of thing for powers of cotangent. I'll leave that as an exercise for you. Now here's a case where we use change of variables, but it's not obvious. Suppose I want to integrate secant x. Well, that ends up being 1 over cosine x. And it's not obvious how to make a change of variables. And that's because there's a trick that we have to do. We have to integrate by secant x plus tan x over itself. I'm sorry, we have to multiply the integrand by secant x plus tan x over itself. And then we notice that the numerator we let equal u, and the denominator happens to be du. And so this integral now has the form of du over u, which we know is the natural log of the absolute value of u plus c, and we get our final answer. This is a good problem to practice as an exercise, just to make sure you understand how this is working. And I claim the same sort of approach can be used for integrating the cosecant. We can also do powers of sine and cosine using change of variables. So suppose we have the integral of cosine to the nth power times sine of the nth power, where m and n are both natural numbers and they're both not even. Okay, that's very important. And so let's just assume without loss of generality that m is the odd power. So I'm going to write this as 2k plus 1. Okay. And I notice that I can go ahead then and I can rewrite a sine to the mth as sine to the 2k times sine. And now what I'm going to do is I'm going to write sine to the 2k as sine squared to the kth power, and I'm going to rewrite sine squared like this. And I notice that this portion of the integrand now only involves powers of cosine. And this is the derivative. It can be written as the derivative of cosine. So I let u be cosine x, du is minus sine x dx. And when you do that, you find that basically you get a polynomial in u, which is one of our elementary integrals we can do. We'd have to expand out what 1 minus u squared to the kth power is, but nevertheless we can do that. That's not particularly difficult. Okay. Now, when m and n are even, it doesn't generally fall into a change of variables formula per se, but since we're talking about powers of sine and cosine, might as well cover it. Generally what we use is we use a double angle formulas, and then we're going to use the addition formula for cosine. And you can see it can get very difficult because, for example, if I have sine to the fourth, I'm going to rewrite that like in the example I did as sine squared squared. I'm going to write the square of the sine in terms of cosines and then square that, and then I may have to use I'm going to end up getting squares of cosines, which I'm then going to have to also re-express using the double angle formulas. So it's going to get to be a little tricky. Let me illustrate very briefly. Suppose I have sine to the fourth. Okay, I'm going to rewrite this as sine squared x squared. I'm going to write this as, and I can do this a number of different ways. I can rewrite the sine squared part first. Okay, and I can see what's going to happen here. I'm going to get a constant term. I'm going to get a cosine 2x term, which I can do by change of variables. And I'm also going to get a cosine squared of 2x, which I can then reduce down using this formula and change the variables again. Okay. So this is a very good integral to practice on. I'll leave this for you to do. The last case in which we use change of variables a lot is on these things that we call the inverse trig functions. And there's three different general forms that can occur. The first is the integrand being 1 over the square root of a squared minus x squared. And notice the change of variables we make. We don't write u is equal to something. Instead of writing u is equal to a function of x, we write x is equal to a function of u. And the specific function that we use is a sine u. And it turns out when you make this change of variables for x and you do the integration, you end up getting arc sine of x over a. Okay, and I'll leave that as an exercise to do it. It isn't hard to do. The second form that occurs a great deal is when the integrand is 1 over x squared plus a squared. In fact, we see this when we work in probability theory with the Cauchy distribution. And the change of variables we're going to make here is x is equal to a tan u. And I claim that when you do that, the answer ends up being arc tan of x over a. So you can see why these are called the inverse trig integrals, because basically the answers end up being inverse trig functions. The last form is more complicated. The integrand is 1 over x times the square root of the quantity x squared minus a squared. And here the change of variables we're going to make is x is equal to a secant u. And when you do that, you're going to find out that the answer ends up being 1 over, and this is actually going to be absolute value of a, times the arc secant of x over a. And again, these are good integrals to practice on, just to check and make sure that you're knowing how to do the change of variables correctly. Okay, and that's pretty much the major integrals we do with change of variables. There are others, but these cover pretty much the main ones.